Okay. So, chapter 5 is really the first part of this chapter, or it's the first part of this class where you have to use a lot more mathematical reasoning, much more math heavy. And so, but the first thing you guys need to understand is that gases what's this focusing on? No. Oh no, that's not good. Okay. Okay, so sorry everyone for the technical difficulties. I have no idea what happened there. But the first thing that's very different about most of chemistry, at least when it relates to gases, is that gases have their own kind of properties. That's what makes them a gas. And what's really cool about them is that a few things. One, they have no shape. Right? They have no shape. No fixed volume, meaning their volume can change. And they're highly compressible. And so this is why you can do all this type of unique chemistry with gases, because they essentially can be moved and manipulated more than any other kind of matter there is, okay? And so what does this have to do with anything? Well, this helps us understand the kinetic molecular theory of gases, which is basically every assumption in the kinetic molecular theory, so I'm going to abbreviate KMT, tells us what we can do mathematically and how we can mathematically describe what gases do. But but before we move on to the math, we need to cover at least, it's called the 5 postulates of a kinetic molecular theory. This is the assumptions that scientists have made over the centuries that have helped us simplify our math, simplify our science, so that we actually understand what's going on. And the first one is that gas particles yeah, sure, we can use it. They are extremely small. And what this means is, or at least relative to, so gases are mostly empty space. Oh, sorry, yeah. You guys are probably gonna tell me that. Okay. So, they're mostly empty space. And this is the important one. Their individual volumes are negligible compared to container. to this one is particularly important because now we can actually simplify our math by just looking at the volume of like multiple particles of gas instead of looking at individual one particle, which is amazing. Okay. And a lot of really easy exam questions I've seen last quarter deal with, do you understand these basic assumptions and concepts regarding gases? Okay. Number 2, gas particles move in constant, random, and straight line motions. If you remember from your discussion worksheet a few weeks ago, one of the big things that was covered is this statement was put verbatim on your discussion worksheet to see if you understood that what you had to replace here is random. So random was the big thing they wanted to highlight. And so all these words matter in this one. Okay? 3, collisions between gas particles are elastic. Which just means like, they use the billiard ball example, right? I use a car crash example for some reason. But the billiard ball example, okay, is that an elastic scattering, or elastic collisions, it's just 2 billiard balls hitting each other and going back. Same energy. An inelastic with IN is energy exchange. Okay, so that's different, and that becomes a really important assumption, at least when you're trying to understand basically what's that one called? The rate of diffusion is one of them, and the ideal gases. Okay. And then there's 2 more. There are no intermolecular interactions. So you can think of this as all gas particles they move along how they want to. They're not affected by their neighbors at all, whether it's attractive forces or it's repulsive forces. Okay? And this is my favorite. The average kinetic energy, depends only on temperature. And then in Kelvin is a caveat here. Okay. And so with that comes our first equation. The kinetic energy average equals 3/2 RT. Where the R represents the gas constant. So this is the gas constant. Oops. The gas constant, which is 0.08206 liters atmospheres. Not true, I'm sorry, excuse me, not that one. It's the 8.3141. Because the kinetic energy is measured in joules. So this has to be joules for this to be joules. And then temperature is just by itself in Kelvin. Does that make sense? So these big assumptions are stuff that you're going to be tested on your exam. I guarantee at least one question is going to be something about this. Whether do you understand the assumptions or do you understand the equation? Okay. Yeah.
So this is the same gas constant as like the 0.082 when it's converted into joules?
Yes.
And what's the unit of the other one?
Liters atmospheres.
Okay.
That one, so yeah, that's a really hard conversion to do, and it's kind of
You just
annoying.
memorize this.
I'd say memorize when you use what.
Okay.
And for the most part, you'll always use the 0.08206 one. There's only 2 instances, which we're going to cover like very soon, where you'll use this one.
Okay.
This is one. Just checking my email section was locked outside. Okay. Okay. All right. So then, once we start introducing, what are the different properties of the gas, what kind of assumptions we make mathematically, we do have to understand one very important thing that gases do is they create something called pressure. Okay. So pressure at its core is force over some amount of area. Okay. So if you ever heard of PSI, for example, this is the American way of saying pressure, especially in tires. PSI stands for pounds per inches squared. So pounds is a force, inches squared is an area. How basically everyone else in the world does it is newtons over meters squared. And that is also known as a Pascal, PA. And so it's really, I think it's very worthwhile actually trying to visualize what pressure means, right? And so if I have a canister of gas, and here is a little gas detector. What pressure literally means is one gas particle hitting it and bouncing off, and then another one hitting it, bouncing off. And the pressure then is dependent on how many gas particles hit that detector at one time and how dense they are. Okay. So pressure literally means how many times is this detector being hit, so pounds, and how large that detector, inches squared. That's what pressure literally means visually, if you're trying to identify what that means. Okay. And so that also means, right, which we're gonna get to this a little later, but if you remember from the ideal gas law, why does volume go, if volume goes up, why does pressure go down? Well, it's because now the gases have more area to spread around them. So that detector is going to be hit less times because the space they occupy is so much larger. So that's where that comes from. That sort of visualization is where that comes from. Okay? Okay, so I also find it very important. I don't remember if Farhad's going to give you the conversion factors between the different units of pressure. I think someone said he was, right? Can you guys confirm that? No? I mean, it would be worthwhile. Honestly, I mean, you can. But it just a quick refresher. I'm not gonna go over these too much, but just because I have them. Okay, what is it? So you really want to get to ATM. That's really that's the pressure you want, or the unit of pressure that you're gonna use for the rest of the chapter, really. And then what's the other one? 1 ATM equals 1.13. Okay. And so all these those are the different conversion factors, the most common conversion factors that I think is just worth having somewhere in your brain. I do recommend asking I could actually ask Farhad right now, but if you see him before me, ask him, hey, what are we gonna get on this test? Okay. Okay. Any questions about pressure? Right, so now, once pressure is kind of out of the way, once we understand what pressure is, then we can start talking about the gas laws. Okay? Because the pressure is such an integral part of the gas laws, then now we can start talking about them. And so the 4 different properties of a gas when it comes to the gas laws. There's 4 of them. You've probably heard of them. There's temperature in Kelvin. There's R, the universal gas constant, which we know as 0.08206 liters atmospheres, mole Kelvin. There is volume, typically in liters. Pressure, typically in atmospheres. And then you have the actual gas itself, the moles. Okay? So all these different things kind of come together to create the gas laws. And I think it's worth understanding at the very least that the gas laws, where they kind of come from, is the understanding that the kinetic molecular theory of gases kind of informs our understanding of how ideal gases and real gases work. Because at the end of the day, these things, when we get to the ideal gas law, there's a lot of assumptions that we make that are from the original assumptions from the kinetic molecular theory. So, with these gas laws in mind, I'll do that. I think it's easier to do this. Okay, so we'll do a survey instead of my math way that we did in discussion. We'll do the survey way. And so what that means is we'll introduce the gas laws one by one and then build up to the big one. So the first one is Boyle's law. Okay, so Boyle's law is the infamous PV equals PV, or P1 V1 equals P2 V2. Okay. Now, what's important here, other than the fact that, yeah, you can plug this in mathematically, and this is a relatively easy equation to do, what happens conceptually is something that's going to carry with it throughout the rest of the quarter, right? Because what is this actually telling you, right? Yeah, it tells you mathematical things, but it also tells you about, you can start predicting things without actually knowing the values of stuff. So if my pressure, what this means is the pressure is inversely proportional to the volume, which means that if my pressure goes up, my volume goes down. Okay? And this sort of motif here, where the two variables are right next to each other, that will always mean that. Okay, so when we see, we'll go to the next one, but I'll show you what this means is if we increase pressure, we decrease volume, and vice versa. And so when we think about the kinetic molecular theory, as I was saying, right, is if your volume goes up, that detector, wherever that may be, is going to be hit less because now the gases have more space to travel in. And now if you compress the system with a smaller volume, now the detector is going to be hit more, so the pressure is going to increase. So if you decrease the volume to a smaller space, those gas particles are going to be there jumping around more, hitting the detector more times, thus increasing the pressure. So that is the conceptual idea of the gas laws. And then really quickly, if you're more of a math person, I personally like these graphs. So if you're in pressure, there's pressure, and here's volume. Okay. What it looks like is, okay, at high pressure, you'll have little volume, right? So one point would be there. And then at high volume, we have low pressure. That makes sense. And so what it looks like is like that. It looks like a hyperbola. That's just if you like to kind of visualize it more mathematically. But yeah, so there's that. And then I will write it a really quick note. I'm going to call it connection to kinetic molecular theory. 1, particles in high volume collide less frequently. So that's Boyle's law. Any questions about that? No? Okay. Okay. So then we move on to Charles' law. Charles' law. This is V1 T1 equals V2 over T2. And kind of cool, the pressure is proportional to the temperature. Okay? Also, really quickly, I know it's kind of tempting, but temperature is always in Kelvin, and honestly, at this point, just always convert it to Kelvin. You're always gonna need it in Kelvin anyways. Don't be tempted by not putting it in Kelvin. Okay. So, what this means is that an increase in volume, you get an increase in temperature. Okay, and vice versa, and vice versa. Okay. So this is kind of hard to visualize, but a hot air balloon example. Okay, I don't know if you know how the hot air balloon works, but basically, yeah, we'll do hot air balloon. Basically, hold on, guys. Let me show you my masterful drawing skills. Give me a second. Oh wow, I don't even know what that is anymore. Anyway, hot air balloon. Okay, so you have a person here. Sorry, I have a person here, and this area here. If you had a microscope, a really tiny microscope, that's all air, right? And so what the person does, or how it works, is that there's a little flame here that heats up the air right below the balloon. What that does is heats up the air, right? But according to this law, what else happens? The volume of the gas increases. So that's what causes the balloon to blow up and to lift up. So that's Charles' law in the real world, is hot air balloons. So, yeah, so an increase in volume. So the really important part, just because we're here, is see this motif of a variable divided by another variable? Those two variables now are proportionally linked. So that's what that little fish sign means. And so an increase in one means an increase in the other. And then the same way for a decrease. A decrease in one means a decrease in another. And so that same motif is always going to carry on for the rest of the quarter. And so, yeah, that'll be cool. Right. Another cool thing, if you're also a math person, I'm going to write this down just because I thought it was interesting. So temperature, if you divide by 0, which you can't do that. You can't do that mathematically, right? So what does that mean? So there's this theoretical temperature that no one has observed yet called 0 Kelvin. That's what absolute zero. That means when everything stops moving. Never been observed ever. It's kind of scary to think about because even at the coldest temperatures, molecules still vibrate just a little bit. But at 0 Kelvin, which is 0 here, everything stops. But no one's seen that yet. So it's a theoretical value, which is cool. But yeah, that's just something cool about chemistry. All right. And then we get into, so after this gas law, there's another gas law. There's 4 of them. You have Gay-Lussac's law. Okay. This one says that the pressure of a gas is proportional to the temperature of a gas. Okay? And what that looks like is that P1 over T1 equals P2 over T2. Right? And so, if you increase in pressure means an increase in temperature. Okay? That's all I want to say. Yeah, so a really cool example of this guy is gas canister. So I don't know if you've ever played, I hope you haven't. Have you guys ever played with like hairspray or anything? Have you ever tried heating it up? So if you heat up hairspray, because it's in a sealed canister, the canister will blow up. That's exactly what's happening. The pressure, if you heat it up too high, the pressure gets so intense that the gas needs to escape and it blows up. And so that's where that law is applicable. And so, because we didn't do it the last time, what this looks like, you should be thinking about this, is when you look back at the KMT, what's actually going on is that now there are harder collisions, right? So as you increase the temperature, more collisions are happening. And then now there is more kinetic energy, or more kinetic energy average. So as you increase the temperature, you're also increasing the average kinetic energy of your gas sample, which is cool. Okay. And then finally, probably the most boring one is Avogadro's number, or Avogadro's law, which states that the volume and the number of and the moles of gas are proportional. Okay, and this is V1 N1 equals V2 N2. And so this one can be used often. The thing is, this is only applicable if somehow only applicable if temperature and pressure are constant. And that gets kind of difficult to do, like in real life. But understanding that that might happen is a total possibility, okay? And this is kind of cool, right? If you add more gas into a chamber, think of the gas as almost like pushing up. This is actually how pistons work. So if you have more gas, you actually push up the piston, and that creates, well, combustion, I suppose, helps in the combustion process. And so all of this together then gives us the combined gas law. And so this is the important one. Okay, because from the combined gas law, you guys can get pretty much to any other equation. So you have P1, V1, T1, okay, equals P2, V2, T2. And as you can see, it's literally just the combined laws into one, right? And so that's why when I was doing discussion, I thought it was very important to start from the beginning, because from the beginning you can get to anywhere else you need to go. But that's the combined gas law. So on an exam, what you're looking for here is look for 3 variables. None should be moles or grams or anything that actually gives you mass units. So moles or grams should not be one of those variables. Because, as you will see in a second, if you do have moles and grams, you have to use something else. And that introduces us to probably the most important law in chapter 5, the ideal gas law, or Pevner, as I'm going to call it. Okay? And so now Pevner relates everything else. It relates everything, including moles of gas. And so, I mean, we've been introduced to all the different types of variables, but I did want to say that if you look at what all we've done with the different laws, we can now kind of create little predictions based on a lot of things. And so, because we've covered a lot of this, all you really have to know is that Pevner is the most important equation in this chapter. If I'm being honest, if you don't know how to do a gas law problem, probably try this first. See if you can fit your equation into this somehow, because that's going to be the most important equation in chapter 5. Right. Any questions so far? Nothing? All right, so that's the ideal gas law. Yeah. All right, so this is a really tricky little one. I don't personally like these, but I have seen it asked on exams before. But this is more of this isn't necessarily a lecture thing, but more of a problem solving thing. So there's this thing called the molar volume of a gas. Okay. At STP, the problem will say at STP, or standard temp and pressure, which are So if your problem says at STP, which is standard temperature and pressure, okay, the standard temperature is 273 Kelvin, and then the standard pressure is 1 atm, okay? So if it gives you those different conditions, then 1 mole of gas, of any gas, is 22.4 liters, okay? And then you can convert this thing into a conversion factor. So if your problem asks you that, okay, what is the volume of certain amount of, let's say what is the volume of, I'm gonna just say methane, it doesn't even matter what gas. What is the volume of methane? Sorry, let's go 2 moles of methane at STP. Then all you would have to do is 2 moles of methane times the 1 mole of gas, 22.4 liters, and that's going to give you 44.8 liters of, well, I guess, volume of gas. Okay. Does that make sense? Yeah. So this is a shortcut, I guess. It's a shortcut at some point. Sometimes the question is going to ask for it, but knowing this conversion factor is pretty important. That's it. Okay. Okay. Cool. Yeah. All right. So these are more problem solving. So so from the ideal gas law, you can get one thing, which I've seen tested on also before. From ideal gas law, you can get the molar mass and density of a gas, okay? This is actually a really good problem solving technique to see if you're paying attention. And this equation, I could derive it, but I'm gonna just be straight up. What this is you have the density of a gas equals pressure times the molar mass of a gas divided by RT. Okay, so D equals density in grams per milliliter. M equals molar mass in grams per mole, and all the rest are exactly the same as they've been. And you can derive this from the ideal gas, actually. You can ask me if you have a question about that. I can do that for you, but I guess in the test sense, it's probably better just to memorize the equation than to try to derive it. But you can derive it. It's pretty easy to. Okay. All right, any questions about that? Okay. All right, now finally, before we start moving on to more kinetic molecular theory, the last thing I really want to talk about here, let's see here. Let's go. Let's do that. Okay. Does that make sense? Yeah? Okay. All right, so now that we understand the ideal gas law, we can use the ideal gas law to describe multiple gases in a mixture. And this is actually where John Dalton derived Dalton's law. Dalton's law. And it's specifically called Dalton's law of partial pressures. Okay. And in this law, what it states is that the pressure total of a system, the pressure total of a gas mixture, equals the pressure of gas 1 plus the pressure of gas 2 and then so on and so forth, according to how many gases there are. Okay? So that's ultimate Dalton's law of partial pressures. But since then, we've been able to derive many more equations that kind of complicate everything. Okay? Now there's this equation that I do not know the name of, but it's a pretty important one. And it states that the pressure of gas, we're going to call it gas 1, doesn't have to be gas 1, it can be whatever gas it wants, equals the pressure total times x, or x of gas 1. Okay? So what is x of gas 1? Okay. The x of gas 1 equals the moles of gas 1 divided by the moles total in mixture. Okay. So when we're doing a law of partial pressures problem, which I think we have somewhere here, which is important in my opinion. Yeah, so something that I think is important to kind of note is, so this is your discussion 5 worksheet, and question 18 deals with this. But I think what I really want to mention here is that these things can be PV, right? PV equals nRT, can be labeled differently according to what you're trying to find. Okay, so if I'm trying to find, in this case, it gives you volume total of the flask, gives you temperature of the flask. So you can do pressure total, volume total, equals moles total. R stays the same for anything, and then T also stays the same for everything. Okay? And then you compare this to something like pressure of gas 1, volume of gas 1, moles of gas 1, RT. So when you're doing these kind of problems on an exam, if the question asks you to find the partial pressure of a gas, and then they give you the pressure total of your gaseous system, okay? What you can do is you can use a PV and find the different variables and the different values according to what you're trying to find. So don't mix up pressure total with the volume of, or don't mix up pressure total with the moles of gas 1. They're two different things that need to be used in two different equations. Okay? But what you can do is you can do, okay, the pressure total and the moles total, and from there you can try to find an equation that stays constant for this one. And so this is kind of the big thing that I think I got confused as an undergrad, is this exists. And I just wanted to highlight that this is important, because you can use PV for multiple different things. You don't just have to use PV for total, you can also use PV for gases, like individual gases within a system. Okay? Make sense? Okay, so there's Dalton's law of partial pressures, diffusion, conceptual John Dalton. Yep. Okay. So before we move on back into kinetic and molecular theory, the last little tidbit I want to give you for an exam question is what happens if you so this is gases collected over water. So if your problem says a certain gas was collected over water, how are you going to approach that problem? Okay? What you should immediately think of is that the pressure total of what I'm going to call water, H2O plus gas, equals, guess what? It's the pressure of the gas plus the pressure of the water. Okay? And then if you solve this for a whole bunch of, you can solve this, one way you can solve this is that you can actually find the pressure of the gas simply by doing the pressure total minus the pressure of the water. And there was a problem somewhere I saw, which could be here. Yeah, it's right there. Okay, I'll let you look at that. But problem number 20 talks exactly about that. So the way you would solve it is by trying to solve for the pressure of nitrogen equaling the pressure total minus the pressure of water, and then from there it gets much more easy because all you have to do is plug it into Pevner after that. Okay, so that's actually how you start that kind of problem. That was kind of jarring for me when I first saw it, but I thought it was a lot easier when I actually solved it. Okay, cool. Yeah. Okay. All right, so yeah, might as well just keep going. All right. The next big lecture topic is going to be ideal gases versus real gases. That's nice, real gases. All right. Ideal gases versus real gases. So the ideal gas model has its own assumptions. Okay. So now, just to make it clear, we have the kinetic molecular theory of gas assumptions, and now we have, as a subset, the ideal gas theories. And so, what that looks like, there's four different considerations. One, particles have zero volume. So as we know, a gas particle is matter, so it actually does have a little bit of volume. In real life, it has some volume. But our assumption here is that to make our life simpler, we say it doesn't have volume at all. It's just a conceptual point, is what it's called, a point, or it's called a point particle. Okay? Number two, there are no intermolecular forces. So this was another one that was reiterated from the kinetic molecular theory of gases. No intermolecular forces. We also have now elastic collisions. And then finally, probably the most intuitively, is ideal gases follow the behavior. So they follow the ideal gas law. PV equals nRT. Okay, so those are the big concepts surrounding the ideal gas. Okay? So then where do these exist? Okay, so this little subset is called conditions for ideal gases. Conditions for ideal gases. Number one, it's high temperature. Okay. Why, you might ask? Well, it's because particles move faster, right? Because we've already seen that, right? Average kinetic energy is based off of temperature, right? So particles move faster, and thus they also have less time to interact. So if you're moving a lot faster, your collisions are more elastic and you don't really interact with anything. Okay, so those are the conditions for ideal gases. Oh, sorry, one more. One more. It's going to be low pressure. So high temperature, low pressure, and I guess with that goes high volume as well. All right? And then low pressure for the exact same reasons, right? Particles have less chance to interact. Okay. Does that make sense? Yeah. Cool. Okay. Now, so that's basically the rundown of an ideal gas on a conceptual level. But now what happens to real gas? So what are real gases? So then that goes into real gases. Okay. Real gases, which I haven't used a different color pen. Real gases. Okay. So real gases, they have a finite volume, meaning their volume exists. They have a finite volume, and they experience forces. Experience intermolecular forces. And so, you might, with you might have surmised that the conditions for real gases are actually just the opposite. So they exist at low temperature, high pressure. Hmm. Yeah, sorry. Yes, so those are what real gases are. Makes sense? Yeah. And finally, this is, I think, also. And finally, really quickly, this equation that I'm writing here, which you're not going to see yet. Okay. That is the real gas equation. You're not going to use the gas equation. I can guarantee you. I doubt Farhad's going to make you actually use this equation, but it's important to understand what's in here. Okay. So this guy right there, that is that's your pressure correction. Or to make it more unifying, what this is remember remember this one right here, that real gases actually experience intermolecular forces. You can think of this as an intermolecular force correction. This is actually, as particles move around in solution, this is them colliding. So I'm going to call this the collision factor. Right? And you add it now because in real gases, things actually do collide with each other. Okay. And then finally, this guy here, this is your volume factor, which accounts for the volume now of the real gas, which is the other assumption that was made up here. All right. And so, like I said, you won't need to know how to do this, like mathematically, what these variables mean, but knowing that these different factors exist and why they exist, potentially maybe ask the exam. All right. Any questions about ideal and real gases? No? Okay, cool. All right. And with that, yes.
If you increase the temperature, the speed of the gas molecules increases, right? But then that decreases the pressure, or not?
Okay, so if you increase temperature, you're saying that the energy decreases or increases?
I'm not really sure.
Okay.
Like, wouldn't like, let's say you have like a container with a sensor, wouldn't the molecule hit the sensor more? So then wouldn't that mean the pressure increases?
Yeah. So that's exactly.
Okay.
Yeah, that's the law. Yeah. So if pressure increases, temperature also increases. I do think. I think that's Gay-Lussac's law. That's exactly what happened. Yeah. If you increase pressure, temperature also increases.
Okay. Never mind.
Okay. Yeah, and similarly, actually, if you rearrange the equation we were talking about, right, the kinetic energy equation, you'll see that the kinetic energy average is actually, if you solve it, right, it's going to be, you see that exact same motif comes back up.
Okay. But then how does for the equation for the real gases, how is it like low temperature, high pressure?
Oh, those are like, those are like the environment around it.
Yeah.
So under these environmental conditions, that external pressure and external temperature, this is how the gas behaves.
Okay.
So in theory, you can think of it like saying, okay, I have hydrogen gas.
Mhm.
I put it in an ideal gas environment. It'll behave like an ideal gas. But then I take out the hydrogen, put it in a real gas environment.
Uh-huh.
Then it's going to behave more like a real gas.
Okay.
Yeah. Cool. Yeah. Okay. So chapter 5. Okay, and then finally for chapter 5, let me get to the big ones here. These are the last parts here, where I want to talk about stuff that you'll definitely be tested on. Which is no, not that first. Okay. Okay, so all right, so from the from kinetic molecular theory, we see a few different things. All right, we've already determined that gases move. Oh yeah, yeah.
So between like the ideal gas and real gases, does it change, like, you know how we did like the gas laws before that?
Mhm.
Does it differ on how we use it for ideal gases, or like how can we, like, what's the difference? How can we differentiate?
Yeah, real gas. So real gas laws. One should. I doubt you'll ever use real gas on the exam, like mathematically, which is great.
Okay.
Because the equation. So you know how like you have like PV-nerd and then you have like PV.
Yeah.
Sorry, like Dalton's law. All those little smaller laws.
Yeah.
They don't apply at all to real gases.
Okay.
Those look much different.
Oh,
They look harder, and they
so
involve
there's not,
calculus.
there won't be like a question on the exam where it's like, use like real gas. Like everything we do is like ideal.
Ideal, right? So
Okay.
mathematically, yes. But I have seen at least 2 questions on the exam talk about the factors. So you know how you had the
Okay.
what was one of them? The volume factor, and the other one was the collision factor.
Yeah.
So I've seen 2 questions asked on, like, I think one of the questions was why does the real gas law include the volume factor?
Okay, but it will be mathematical.
No. You will not have to know that mathematically,
Okay.
unless you take a physical chemistry class.
Yeah.
That's where you have to use that.
Thank you.
Yep. Okay. So from kinetic molecular theory, we see that gas particles move in constant random motion, right? But the big thing here is, this is a very important point, is that temperature, right? We know this because I already showed you the equation. Temperature controls the average. I'm going to write this one out. Average kinetic energy, not individual speed. So this is an important point. I think Dr. Farhat might have shown you about this. But what that basically means is that not all individual gas molecules move at the same speed. And then we could extract from that even further, is that if we look at this visually, okay, where this is velocity in meters per second, and this is, I don't know, gases, like just number of gas molecules. What we see is it looks more Gaussian, okay? And so this guy, the peak here, the topmost part here, that right there is your average kinetic energy. That is what your equation is telling you. So there is a gas particle that's moving at a really low temperature. Let's say you have a solution, right? Or sorry, a canister of gas. So a canister of gas, and you have a few different little particles. What KMT is telling you is that this particle here does not move at the same speed as this particle. And what that means is that at the end of the day, what you really do with kinetic or average kinetic energy is you're taking an average of all the different speeds of the gas particles in a thing, and then reporting that, which, if you, which statistically is the most populated point here in the middle of the peak. Okay, so that is the average kinetic energy. Does that make sense? Does the distinction make sense? So it's not individual. This is the average of all the different particles moving at different speeds. Okay? And so what that gives us is something called root mean squared velocity. Root mean squared velocity, or VRMS. This is mu, it's a Greek letter, or you can just call it V, it doesn't matter, as long as you know what it means. Okay? And so, like I said in discussion, right, root mean squared is a specific type of average where it takes into account all the different speeds and combines them into an average. But I do want to mention, or I do want to make sure you guys know the difference, because I've seen this asked on an exam. So how to just calculate something that's RMS, so root mean square. How to calculate. So this can just be a random set of numbers it gives you. I've seen this at least once, right? One, let's say you have 77, 87, 97, 98. Right? What you do is you square all the numbers, square all numbers. So you get 77 squared, 87 squared, 97 squared, 98 squared. Number two, you take the average of everything here, including the things that are squared, right? You take the average, so that's what? 77 squared, 87, or plus 97 squared plus 98 squared divided by 4, because there's 4, right? And then at the very end, you're going to take square root. So everything, sure. Okay. So just in case you're asked that on an exam, there's this. So that's how you calculate a RMS of anything, an RMS of a data set. Okay?
If you don't mind, do you think maybe we could see this on a calculator?
Sure. Like, you want to see like my calculator screen?
Yeah.
That works. Wow. Okay. Yeah. So 77 squared plus 87 squared plus 97 squared plus 98 squared. To get that number. And then you take the, so I already skipped to number 2. So I already squared them. And now I'm skipping to number 2 where I divide by 4. Okay. And then I take this guy. I might need the square root first, sorry. Second square root. I just click on this number, my answer. So the RMS of this is 90.15, 90.2. Okay. Does that make sense? Okay. And you will see that if you calculate the average, it will be different. Like just the normal average, it would be different. Yeah. Cool. Okay. And so why have I done all this so superfluously? At the end of the day, there is an equation in chemistry called it's called the root mean squared velocity, which is written as so. And I always write in kilograms to remind myself. So this is VRMS equals the square root of 3 RT divided by the molar mass in kilograms. So, like I said, molar mass in kilograms. So this is molar mass, so M equals molar mass in kilograms. So this is a very easy error to get wrong, because molar mass is always reported in grams per mole. In this case, it has to be kilograms. Temperature is just Kelvin. R, here's the only other time you're going to use R with this. This is going to be the joules form of R. And that's it. Those are all your different variables. 3 is a constant. 3 is a constant. And then really quick look at a discussion question, just to kind of reiterate my point. It's all there, right? Get into that? No, sorry. No. Number 4, or number 4. That's what it that's what it should look like. Okay, or at least a very simple example problem just kind of laid out. This is a really easy thing to test on an exam. All right. But does that make sense? VRMS, okay? So now we're gonna look what we've learned from our gas laws to tell us about the different relationships without even looking at predictive values, okay? So what we see here is that the URMS is proportional to delta, or to square root of t. What does that mean? Is that if you increase t, the VRMS is going to increase by the square root of that increase. Okay? So if you increase t by 2, you're going to increase VRMS by the square root of 2. Okay? So, but regardless, what that tells us at the end of the day is another really important concept. At higher temperatures, molecules, on average, move faster. Which is actually also, we've known that from the KE equation. The KE average equals 3/2 RT. We know that exact same thing, okay? But this is just to reiterate the process. But not only that, we know something else. The VRMS is proportional to 1 over the square root of the molar mass. We got that all from the math equation, which we can try to put back here, which probably won't happen. Yeah, won't happen. But okay, we see here that, right, because m is in the denominator, so if you multiply both sides by square root of m, you'll get square root of m here. And what we learned from PV equals PV is that if one goes up, one goes down. So that's where that comes from. That's why it's such an important concept. Because understanding this can be applied anywhere will help you and save so much time, especially coming for equilibrium. Okay? And so what this tells us is that lower molar mass gives us faster molecules on average, which is true. And that's exactly it. And so that should make sense, right? If a heavier object is going to move slower, which is exactly what this is telling you. And we've just proved it mathematically. And so another way to look at this, I don't think I've ever seen this, but just quickly, let's see if I want to actually go into this. The thing is, I didn't see it covered. Yeah, I didn't see it covered. I'm not going to go over. I'm just going to describe it again. Basically, on average, right, if you have more temperature, on average, if it's hotter, on average, it's gonna shift. So let's say this is the Gaussian curve at 60 degrees Celsius, 60 degree Kelvin, right? And this is our average kinetic energy right here. Right? If we get hotter to 90 degrees Kelvin, it's actually gonna shift like this. So now, on average, your gases are moving faster at higher temperatures. Does that make sense? Yeah, so this is just a nice visual representation that's called, this has a name, the Maxwell-Boltzmann distribution, which tells us that as things go faster, on average, molecules go faster. Okay? They're the same thing for molar mass, right? If you're heavier, so let's say this is the molar mass of, I don't know, 44. This is the molar mass of 22. Okay, so on average now you have more energy if you're lighter, and you have more energy if you're at a higher temperature. Okay? So that's what it looks like. That's a distribution. Okay? Makes sense? Yeah? Okay. All right, finally, the last two things I want to cover in this section. We're not going to go too in depth. Effusion. So effusion. This is the passage of gas. Passage of gas through a tiny hole. Okay. And what this kind of means is like if you have a tire, and you prick the tire, and now there's a little hole in the tire, the gas is going to escape over time, and that little tiny hole is where the gas passes through, and that's called effusion. Okay. That's really all you want to know about effusion. The other one it's kind of its partner is something called diffusion. Diffusion is described technically as the movement of gas from high concentrations to low concentrations. So if you've ever had like a perfume or a cologne or something that smells very powerful, and you spray it on, it smells very powerful to you who's getting sprayed on, but eventually if there's a person near you, they're also going to smell it. And the passage of a high concentration of gas near you to then a lower concentration that gets kind of spread throughout the room, that is the process of diffusion. Okay. And then a really quick thing that I saw on the problem, or that I saw in your molecular formula sheet, is it's called Graham's law, which describes the rate of effusion, which means how fast does it actually spread across a room. Graham's law is rate of gas 1 divided by the rate of gas 2 equals the square root of the molar mass of gas 2 divided by the molar mass of gas 1. Right? So this compares the different rates of diffusion among two gases of different sizes. Sorry. Okay, yeah. So, let me write that really quick. Okay, cool. And in that case, you don't need to turn those into kilograms, they fine in grams. Okay. Any questions on chapter 5? That is all of gases. Okay. So if I'm being honest, the two big takeaways from any of this is that if they're lighter, they move faster. If they're at higher temperatures, they move faster also. Those are the two really big things. Okay. All right. Any questions of chapter 5? Yeah.
Why would you use the Coulom's law? Like, what would it what kind of question would be asked that you would use this on?
The one way I could think is I have a bike tire that has oxygen and argon, and I have oxygen and argon, and the rate of argon that's traveling through the room is 391 meters per second squared. Meters per second. Okay. What is the speed of oxygen? And so you should know that, okay, I've given a rate, and then I can use the periodic table to be like, okay, how much does oxygen weigh, which is diatomic. Oxygen is diatomic, so it's not 16, it's 32. And then argon is what, 39? So that actually be pretty similar. But then from there you can find the rate of oxygen. Cool. Yeah. All right. Any more questions, chapter 5? Okay. All right.